and that's what this is all about. You know, try to pick up something new. But I have to tell you, I'm on a mission. I'm on a mission. I feel like a monk that goes traveling. I'm on a mission. What I'm trying to do is I'm trying to change the way labs are done. So I'm on the green chemistry mission, but I'm not like, that's why I found it very interesting, the lecture I just came from, where you have a safety pro talking about, that's why I wanted her to state in public that they're not talking about banning chemicals. They're talking about understanding how to use the chemicals. But, and there's a bunch of goals here that I'm trying to address. But if you could turn your camera on so I could see your face, so I could see if I'm making you bored or making you smile or laugh, I'd appreciate it. This way, it jacks me up to even project even more. All right.
Okay, hey,
so,
Mark, I get to introduce you. So you're going to have to stop talking for a second so I can introduce you. But you know what? I realized, is it Langella? How do you say your last name?
See, now you can tell that you're young, you see? So if you span the group, there's somebody in here who's going to remember me as Frank Langella because they remember that good-looking actor that played Dracula. He was like the first Dracula. See, Gene's not in the head. See how she's in that era. And they always mistake me for Frank Langella, but I'm really Marsilio Mark Langella, like the actor. And then they always ask me, do you know Frank? And I go, me and Frank are like this because my father's name was Frank and my son's name is Frank. So that was the joke for like a decade because it's Langella. It's Langella.
Okay, awesome. All right, so let me just, I'm making Rochelle co-host as well. All right, so let me just quickly introduce you. Mark Langella is currently an AP chemistry instructor at Mahopac High School in New York. He is presently an adjunct education professor at Manhattanville College and adjunct chemistry professor at Westchester Community College. He received a BA in chemistry from Manhattan College and an MA in science education from Lehman College. Mark Langella has over 30 years of experience teaching AP chemistry and is a College Board AP chemistry consultant since 1994, as well as a College Board workshop coordinator. Mid-Hudson section of the Chemical Society has chosen Mark as the recipient of the Excellence in High School Chemistry Teaching Award. He is also the founder and director of the Putnam-Westchester Industry and Teacher Alliance and has been a coordinating board member of both the SUNY Purchase Alliance of Chemistry Educators from 1990 to 2000, as well as the Teacher Center of SUNY Purchase from 1999 to 2002. He's also a developer for Mini Concepts custom designed chemistry lab kits. And I'm sure he'll tell you more about that. And on a personal note, I just want to say that I have had the pleasure of attending many of his demonstration sessions where he's been teaching new tricks, and he is very engaging, and I've learned a lot from him. So we're very, very excited to have you here, Mark. Thank you.
Thank you, I appreciate it. That boy, my dad and mom would have been proud to hear that. That would have been a good one. Okay. All right, so today I have a goal. I want to just try for you to change one of your experiments in a non-pandemic environment to go mini scale. That's my goal. And I want you to understand why, and I want you to reflect on when people put up signs, save the environment, climate change, but they never come up with the one thing, just the one thing that you could do that can help resolve part of the situation. So I've been on a quest going around doing workshops on changing the typical chemistry labs that are done in the college level and non-college level chemistry labs in high schools and in colleges. So we're going to address a concept called mini concepts, okay? And I'm going to create this PowerPoint presentation to discuss why change. Okay, let's quickly talk about why change our concepts. First, let's talk about where our concepts come from. Our forefathers, who was my favorite chemistry teacher, your favorite chemistry teacher, did an experiment a certain way. And out of respect to those, our forefathers, we continued to do the experiments the same way, but they were not teaching in the environment that we're teaching today. So That first, in order to understand where the head go forward, we have to reflect back at where did we get all our ideas? Who are we emulating? Okay. And if we could understand that, maybe we could consider change in one of the experiments that I'm about to share with you. Obviously, green chemistry is the driving force behind this, but I'm not the type of guy who says, okay, let's do chemistry without chemicals. That doesn't make sense. And there are people out there that preach that concept. What my concept is take everything and reduce the quantity, reduce the waste. And the second thing is to recycle. Now, what that means, recycle means, you know, that strawberry container that you purchased at the supermarket. Instead of taking that strawberry container, throw it in the recycling bin. I say take it to school and use it as a container for one of the lab kits. That's true recycling, because the odds of that, you know, I love that commercial with the little girl brushing her hair and and the brush is speaking, going, I knew I'd come back someday as something else. The amount of energy invested to transform those plastics into this new type of plastic or a new application is not worth the time and effort. So it's better for us to take materials and figure out what to do with these plastics. And there's a lot of different, I'm going to show you some quick things that you can do that will change everything, the whole perspective. Time. People, you know, I perform somewhere between 40 to 50 labs in all my classes per year. Someone will say, how do you do that with the amount of time you have? It's because we transformed into mini scale. Everything's mini scale, okay? And that's the first thing I have to address, because I have to do guided inquiry experiments as part of the mandate of the College Board. So I got 6 guided inquiry experiments. Guided inquiry experiments take 3 times the amount of time it typically would take for a normal experiment. To qualify an experiment in my curriculum, you can only use a maximum of 15 to 20 minutes to gather data. Okay, that's all you can use. And if the kit doesn't fit in the box, we don't do the lab. That's the rule. So we're going to take a look at the time issue and the storage issue. Most teachers have a storage issue. We're going to store the labs. I'll show you some ugly pictures on how some of our labs are stored to address. Okay, the other problem is, are they really doing experiments? What do I mean by that? Well, when you do a titration, typically in a titration, there's one student that's operating the burette and the other student standing right next to them. And you're considering that a trial in the experiment when the other student comes over and gives him his opinion or her opinion on where the meniscus is. And when you see we did a trial titration, in mini scale, everyone does a trial simultaneously. So it's 4 trials from one table in 15 minutes rather than 3 trials from one table in 40 minutes. So that's what mini scale can do for you. And again, these dreaded guided inquiry experiments where students develop their own procedure. Well, if you're doing macro scale, it could get a little dangerous and very complicated. And again, what we're trying to do is training. It's training in skills necessary to address the guided inquiry. But we don't want to compromise. Under no circumstance do I want students not reading scales. We don't count drops. We avoid counting drops. That's a concept called micro scale. That's the difference between mini and micro. We still have scales, we're still reading scales. You could do an analysis of your classroom, take an index card out and your rulers and ask them to measure the ruler in centimeters, and they will not be able to do it. In 31 years, I've found that there's 30 to 40% of your students cannot read a ruler. So why would I want to take away scales? Okay, so that's not what we're doing. But we don't want to compromise any analytical technique, try to minimize reducing the exposure to analytical equipment. And in general, what we're doing, we're dividing everything by 10. Okay, that's what's good. So if you're using 1 gram, we're going to use a lot less than 1/10 of it. Okay, so the idea is to eliminate quantity. But to gain, you have to give some things up. Okay, so in my school, in my lab, I know this is gonna drive you crazy, this statement. We don't use graduated cylinders because in the 5th grade, the 6th grade, the 7th grade, the 8th grade, the 9th grade, the 10th grade, they use graduated cylinders. So we don't use graduated cylinders anymore. We don't use burettes anymore. We show them a burette, We do demo with a burette, and then the burettes never come out again. We don't use crucibles. We don't use ediometers. We don't use Bunsen burners only once. We don't use water baths. And we definitely don't synthesize magnesium oxide, the one that our forefathers synthesized and teachers are still synthesizing the same way on a compound. But if you give those things up, I can guarantee your labs will go from 40-minute data acquisition to 15-minute if you just pay attention to the concept. In my school, storage is an issue. So your little kids, how your kids macro scale would be in my school all over the place. You're trying to find somewhere to store. This is a fire hazard right here. So these boxes had to be removed because you have to be over 18 inches from the ceiling. So you can't store kits or in that way. So you have to go mini in order to make the magic happen. So let's take a look at some experiments that we do at Mahopac, and I've been promoting to talk about why. One of the things that we rarely take out is your common everyday thermometer. Because again, if you want to go to advancement, when you ask your students, where do you find the thermometer at your house? The first thing they'll say, in the bathroom or in the medical kit. And that's about it, right? And what about, how's your stove operate? How's your stove measure temperature? How's your furnace measure temperature? How does your boiler measure its temperature? They don't use thermometers because the thermometers would explode. So the first thing we do in my school is we measure temperature using an alternate method. We discuss the ability of metals to conduct electricity and heat, and how metals can conduct electricity and heat, but they all conduct differently. They don't conduct either as well, or maybe they conduct better than a typical piece of copper. Based on that, what you can generate is what they call an electromotive force. Electromotive force is a pushing and pulling of electrons. So using that, the technology in satellites, the technology in your automobile, the technology in a boiler, we can use the ability of metals to conduct heat as a way to measure temperature. So in this activity, for example, students are going to take, basically it's called thermocouple wire, which is what is used in a furnace or a boiler. And they're going to create a juncture where you're going to have two wires that are basically wound together on one side, and on the other end they're together. And you place this in a reference temperature, like 0 degrees Celsius, ice water. And one of the wires that are connected, you're going to cut them and you're going to measure what we call the electromotive force, which we introduce to the students, a device that all students will eventually need to know about, called a voltmeter. So what are we doing? We're moving forward. We're introducing them concepts in physics that are used in chemistry, right? And they learn how to read a voltmeter. And then they realize that this device can measure things that are really, really hot and things that are really, really cold. So what kind of things, this is what it looks like. Basically, you have your little calorimeter here with some ice water. This part is in the room, and you're measuring as a millivolts, 0.7 millivolts, which is basically telling you, 0.7 volts really, is telling you how much electromotive force is being generated by the difference in temperature on the end of this end of the wire compared to the reference on the other side. We have a chart that gives you the conversion of volts to degrees Celsius, and then the kids take that, they convert it to Kelvin, and then they take Celsius, and they even convert to the forbidden unit called Fahrenheit, which, oh, that's not on the Regents in New York. We don't care. I don't care. It's not on the Regents. It's something that they need to know, how to plug in a number into a formula and convert it into another unit. Now, what can you do with something like this? Well, here's an example of a Regent student, a low level student, writing a data on measurements that they took. So here's an example. I took this right off a copy of something I had. We used a typical propane flame and a typical butane flame. And what we showed when we had a luminous flame, which is mostly light, that has carbon in it, that's because of incomplete combustion, you have excited carbon, they measured 34.4 millivolts as the measurement inside the flame. And then they converted that from the chart to Celsius, and then went from Celsius to Fahrenheit, Celsius to Kelvin. Then they show that in a non-luminous flame, you're going to get much higher temperatures, and they need to discover where is that the highest temperature found with the wire, right? Now think about it. You're sticking a wire into these flames to get a voltage, which you're going to convert to temperature. And then we have butane burners that we use typically in place of a Bunsen burner. And we test the butane burner to see what kind of temperature you get from a butane burner. The first reaction we're introducing is combustion in my chemistry class, because that's the most exciting one of them all. And there's a typical chart that they would create from the experiment. Has anyone ever done an experiment like this before? Beautiful, beautiful. So to let you know, this has been around for decades. Okay, the science has been around for decades, and they've been in high school for at least 6 or 7 years. So the question is, what we're trying to do here, we're assessing the ability for students to read charts, we're assessing the ability of students to do conversions, right? And we're teaching students about technology and how to measure temperature, really high temperature, really to low temperatures, because you can't use a thermometer, right? This is like one of the first labs that we do. Another thing that a lot of teachers don't do, they talk about it, they discuss it, but they won't do it because you need some really expensive apparatus that their forefathers showed them in organic chemistry. But I have to tell you that you don't need the type of equipment that you see in the animation on the left. If you go to a moonshiner down south, they tell you don't need expensive organic apparatus to do a distillation of ethanol from some sort of wine. In fact, all you really need is some plastic tubing, and you're in business. So what we do, I'll show you one that's set up at school. What's pretty cool is the students make a homogeneous mixture that contains red dye, blue dye, ethanol, and water. And we're asking them to separate the ethanol from the water in what we call fractions. What's neat about this setup, we have a thermocouple wire that's measuring the vapor temperature of the vapors that are rising up this tube, the separation column, right? And we're measuring the pot temperature simultaneously. Now to demonstrate, now I didn't have a movie on this, so I had to build this in my garage before the workshop. So what I did is, instead of making a homogeneous mixture, I took some homemade wine that I made, and I put that in the pot here, which is the flask, heated up, and with Vernier technology, Vernier sells an interface where you can plug in these thermocouple wires, and you can record the vapor temperature and the pot temperature at all times. And the students get graphs from this technology. And what we end up doing is we end up separating the ethanol in fractions in this collection tube that's sitting in some ice water. So what happens is, again, you're going to get condensation. The vapors will rise based on the rate of evaporation difference between the chemicals in the mixture. In this case, it's the ethanol leaving the aqueous pigments, flavonoids, all the cool stuff that's in wine that's good for you. We're separating the ethanol away from that, right? And then we're going to collect it in the collection tube. Where you can see the example of grape, my homemade grape I made in the experiment in my garage. That's how simple it is to do distillation. And all you need is some plastic tubes. The plastic tubes are typically be fluorinated polymers that can resist high temperatures, like close to 150 degrees before they deform. The other important thing is chromatography. Now I'm talking to you from the high end. What do I mean by that? I have taught every single level of chemistry that exists. But I've spent a tremendous amount of time now as a consultant teaching advanced placement chemistry. And what I'm trying to tell you is, it's a mandated question now, chromatography and distillation, on your general chemistry class. That was not always true in college, but now it's a big deal. So the more you expose the kids at lower level chemistry to distillation and chromatography, the stronger the student will be able to answer questions at the collegiate level. So a lot of teachers do paper chromatography, that's cool. A lot of people do thin layer chromatography, that's even better. But in my class, since biology is doing paper chromatography, right? or thin layer chromatography. Why would I do the same experiment at my level? So I typically made a simple column chromatography separation that the students can do. How it works, you can either pack your own column. I made this really concentrated so you can see the different colors. Most teachers don't do this experiment because they don't want to whip out a vacuum pump. But that's how our forefathers used to do it. Or an aspirator. You don't need that. All you need is a big syringe to act as your pump. So in the picture, this is all you need as your vacuum pump. This is your sidearm flask that you might have at school. You probably have them sitting in a drawer, not being used. This is a one-hole stopper. This is silica. And this is like purple Skittle dye that you have in here. And you're separating the blue from the red, depending on the eluent you use. And here's a schematic of what the student is. You can see it's a student writing this. I saw somewhere he wrote silicone instead of silica in one of these drawings. The goal is to separate the blue dye from the red. So they collect the blue dye in a vial that's sitting in the suction flask. We've all seen this. Where do we see it? In college. What I'm telling you now, it's got to happen, is some of this stuff's got to happen in high school. We talk about electron transitions in high school, right? And right away, we jump into these experiments like flame emission spectroscopy. We don't do that in high school. We start out with electron transitions. We talk about each particle that's in an atom, the fact that they have kinetic and they have potential energy. So the first experiment that we do is we talk about the transition of an electron from high potential energy to low potential energy. So how do you do that? Well, they're called light emitting diodes. And the LED light, the little Christmas holiday lights, right? So I built these things called exciter boxes where you could stick an LED in it, and like basically it's a battery holder with resistors connected to a connector that you could stick your LEDs in. There's different styles, different flavors. But what we're doing is we're talking about when an electron goes from a high energy state to a low energy state, it spits out a particle called a photon. And you can easily calculate the energy of a photon by doing an experiment. Let's see if this works. Is this why you asked me about the video? I think this is why you asked me about the video. Let me make sure you can see this. Hold on. Go to the Zoom. New share. Let's go to the video. Can you guys see this video on your screen? Okay. So here's one of my students. Her function is to find what is the energy of these LEDs. Okay. Now this is in this experiment. This is an old video. How do I know it's an old video? Because this is the prototype of what I built right here. She has different LEDs in these containers. And what she has to do is figure out, one, what is the energy of the LED? The way you can figure out the energy of an LED is real simple. You put it in one of these exciter boxes and you measure the voltage, what they call the voltage drop across the LED. So if you take a voltmeter and you put the positive and negative across an LED while it's lit, you get what they call a voltage drop. That's the voltage that's being converted into energy to light the LED. Well, we teach a concept in class, but you never ever tell the students why you need to know this. Does anybody know that scientist called Millikan? What did Millikan give us? Yeah, you can push the talk button. It's like you're in class. What did Millikan teach us?
Was it the charge of the electron?
The elementary charge of an electron. Well, if you take the elementary charge of the electron and you multiply it by the voltage drop, which is the voltage across an LED, that equals the energy of the LED. So with that number, now you could actually use that in class. You light one of these LEDs and say, you know, Millikan, he gave us the elementary charge. If we take that and we multiply it by this voltage across the LED, we can determine the energy of the LED. Where's that energy coming from? Because inside an LED, you have electrons in a higher energy state being pushed off a cliff to a lower energy state. When they drop, the energy comes out of the LED. So with that, the students can calculate what is the frequency of the light, and then they can calculate what the wavelength of the light with a thing called math. Okay? Now, what's cool about the experiment is in my lower level kids, the exercise is to teach the kids how to use scientific notation, because all the numbers that plug it in are in scientific notation. So you know when you teach about scientific notation, the kid nods his head, yeah, and then you give them a quiz on it or a test on it. They either fail or they get it right. Instead, in my class, we use the LEDs to get them excited about doing the calculation and then placing the LEDs in order of their energy. You know how you teach the kids about the famous electromagnetic spectrum in the visible range? My kids don't do that. They use the LEDs to create their own spectrum and say the red light has lower energy than the violet light. How do you know that? Because I proved it with the math, Mr. Langella. Very good. That is correct. That's how my lower level kids do it. My upper level kids, they're going to do something like this. So in here, you have a student that's using, obviously, technology. She's going to record what they call an emission spectrum. She's going to work backwards because she's advanced. She's going to take the LED and she's going to put it into a thing called a spectroviz. A spectroviz is like those spectrophotometers that we used to use at a quarter of its size, right? So she's organizing her little LEDs by what colors they are, right? And she's got to determine, using the wavelength, go backwards from nanometers to meters. She's going to convert it. And then she's going to figure out how to go from wavelength to frequency. These are all formulas and math. And then she's going to use a thing called Planck's constant to determine frequency to energy.
So
This is real.
Box, you have two wires that serve the same function.
Now, when you put the LED, you got to put it in the correct direction so that the electrons go from high energy to low energy, right? And now she's going to get her little spectroviz. She's going to put the LED right into the spectroviz. And you get this little blimp on the screen. Now this is, you can see there's an old video because that's an old lab quest. They don't sell those anymore.
Hey, Mark.
Yes.
I have those spectroviz, but I don't know, what is that blue thing that
That's
she's...
the thing that lights that's the LED that's lit.
No, where she's seeing that right there.
That's an old lab quest. Do you have lab
Okay,
quests at school?
Yeah,
They don't
okay.
make that design anymore. That's the old Gorilla designs. They were a lot more durable than the ones they make today. But you can use a Chromebook to do this. You can use any technology that you can connect to a spectroviz can do what I'm showing you right now. And now she figured out what the wavelength of the LED is, and she's going to work her way backwards to determine what the energy of the LED is using math. Now the video continues showing you what else can you do. I could fast forward it. You could also, we sell a device that you can plug into the lab quest that lights the LED and records the LED at the same voltage at the same time.
Do we say how much our voltage change was?
Yeah, you can record it.
Okay.
Now there's a lot of lab to this. There's a lot of cool added experiments to that kit. But the key is to teach the kids about electrons at high energy, from high energy going to low energy. We do that because we're trying to teach the students that when you take an atom and excite an atom, its electrons go from a lower ground state potential energy to higher potential energy, and then immediately come back down. So we're teaching them when you excite an electron, you're giving them photons that they absorb. And with those photons, they go to a higher energy state. But when they come back down, they're going to spit photons back. Not necessarily the same photons, but you can record the energy being emitted and use that to determine what kind of atom you're looking at. So we do this before we do all the classic labs, flame emission, all that stuff. And these are the kinds of questions the students would answer in an experiment. Like, what wavelength was the resulting light produced? Put the colors in order from low energy to high energy, that kind of thing. And these are the type of calculations they would do. Now, I know it's hard to believe. That's why I love to have one of my Regents kids, my lower level kids, show you their calculations. But here's the difference. They're only doing it for one LED that they were given in their group. That's the difference. My AP kids will do it for like 6 LEDs. My AP kids would determine Planck's constant. My AP kids would determine what the calculated wavelength is, and then using the SpectraViz, determine what the SpectraViz says the wavelength is. And then they would be asked an evil question like, why is the wavelength off a little bit? Because there's no such thing as a perfect system. You might lose some energy due to heat. That's possible. Now, what makes LEDs really cool, there's very minimal and small amount of energy lost. And that's why they're so energy efficient. But as the wavelengths get small, like green LED would be more off than your orange LED, if you notice. Why? Because the higher the energy, the more chance of you losing some energy due to heat. And like I was saying to you, I created a device that you could plug into your LabQuest and immediately use your LabQuest as the voltmeter and to light up the LED. So you plug them in and it gives you the voltage right away. Now, why would I do that? For my AP kids. Because what my AP kids will do is they'll figure out the energy of the LED and then stick it in the SpectraViz and get the wavelength. Why is that important? We tell them, prove Planck's constant. How did Planck come up with the number? And they emulate what Planck did to figure out what Planck's constant. And you'd be amazed at the values you get. This is what I'm trying to show you. So the SpectraViz will light it, and you can record the wavelength. So you get the voltage and the wavelength at the same time, just by sticking it in the SpectraViz. Here's a raw data. You know, like a scientist will say, oh, look how great my kids did. Well, you can see here that the student had an error on this LED, but the other numbers are in a better direct relationship. When you get the best fit straight line for a data point, you get something like 6.732 times 10 to the negative 34th, which is in the order of magnitude of Planck's constant, even with our error. The other cool thing that I wanted to share with you is how we teach the concept of energy levels. You know, when you teach it long enough, you go through phases of teaching. I'm in what they call the magnet phase. The magnet phase is when you go get magnets, you go stealing magnets off refrigerators and you cut them up into shapes and particle sizes and all that. Well, in the magnet phase, I learned there's a great way to teach Bohr's model, to teach the quantum model. And what you do is you buy magnet paper. Instead of taking magnets off of refrigerators, you buy what they call magnet paper. And on the magnet paper, my students are broken up into groups and they're asked to create what we call the Aufbau diagram, where you got, so this is a magnet board right here. And these magnets obviously are stuck, and on the left represents potential energy of the electrons. And obviously here we have the different energy levels and the orbitals. Each of these boxes represents an orbital. And let's start off with the first misconception that we need to stop doing. I saw someone had an image of Bohr's model as their insignia, right? What's wrong with the Bohr's model? If you look at the Bohr model that you typically see in the 5th grade, 6th grade, 7th grade, 8th grade, 9th grade, that all the circles are equidistant from each other. That is incorrect. So what do? We keep using the same Bohr models and we use them and put models up, images up, but Bohr was a lot smarter than that. Bohr knew that the circles weren't equidistant. The first circle was really close to the nucleus. The second circle was a lot further from the nucleus. But as you drew the circles, they get closer to each other. So when you teach this, please make sure that you teach that to the students in your lower level chemistry classes, because when they go to AP Chem, then their brain cells get blown out. Bohr also was famous because he proved the colors that you would see if you excited a hydrogen atom when the electrons jump from higher energy states down to the second level on its way back down to the first. So all jumps down to the second level, you could actually see the photons with your eyes when they go from a higher energy state to a lower energy state. But you can't see the jumps from higher energy state to the first energy state because those are in the ultraviolet range. And we as humans don't have the chemistry in our eyes to be able to see that. So what we do is we tell them, you see these little boxes? Bohr didn't know they existed. But Bohr knew and thought that electrons can sit in what we call these energy levels, these rows. So he predicted if you excited one electron up to one of these higher rows, on the way down, what are the possible colors you would get from 6 to 2, 5 to 2, 4 to 2, 3 to 2. And he proved it mathematically with a constant called Reinberg's constant. But it turns out what Bohr didn't know and what we should be teaching is that these boxes move. What proof do we have that the boxes move? Professors of chemistry. All atoms emit their own colors, right? The reason why they emit their own colors is because the boxes are in different positions for every single atom. What controls where they sit is the nuclear charge, how many protons you have. That's why we teach the kids. Atomic number is a critical thing because that tells you what atom you have. And it would also be directly related to what spectral analysis you would get because it's controlling where these boxes sit. So on this diagram in our group, we show as you add electrons, how do they go into the boxes and how the boxes are going to move. So see how nice they're all in semi-rows right now? Eventually, these will be all scattered into different positions. And the greater your nuclear charge, which boxes are affected the most is the S. Then comes the P's. Then comes the D's, and then comes the F's. And eventually, you get some screwed up situations where your D's of inner electrons are equal to your S's of outer valence electrons. When does that happen? Tamika? When is your D's? Which atoms have that?
The transition metals.
That a girl, right? And she's got to teach that. And that's why your transition elements can lose some of their inner D's with their valence electrons because their orbitals are really close. But you have to tell the kids, these are models. These are for atoms that are non-bonded. Once you bond the atoms, you create new models. You merge the Aufbau diagrams into new Aufbau diagrams called the molecular orbital models. Or if you're metal, we call them the band theory. Now, all that science, all that, now from those boards we do Lewis dot structures, we do ionization energy, we talk about where electrons are, first electron will be removed from, second one will be removed from, electron affinity in AP chemistry we have to talk about. So we talk about if you put an electron in the diagram, where would it go? All that stuff is what we talk in AP Chem. But then you got to say to yourself, Mr. Jell, I don't believe you. Okay, let's do an experiment. Prove me right or prove me wrong. So we're going to do an experiment. Now, I was trying to tell you, in my class, if you don't fit in the box, we don't do the experiment. So here's what we call the Electron Configuration Lab. It all sits in a box. So all the materials in here for a group of 24. Okay, what do you got in the box? Well, each kit, you have tongue depressors that create this little bridge. You have a super magnet. This is like the most, everybody loves this lab because it relates to all the stuff we teach. You got this little cup. You got 6 vials. Notice the color of the vials. They have color, except for one. They're all transition metal salts, right? And then you have this collar made of construction paper with a little paper clip on. We're going to take a balance, okay, your typical Scout balance, and we're going to put the collar around the pan. On the pan, we're going to put the cup and a magnet. And then over the collar, we're going to put our little bridge. And then we're going to put 0 to make sure that the balance records no mass at this point, even though there's items on it. And check it out. We take one of the vials and we put it above the supermagnet, about a centimeter from above it, just like that. And we see some strange information. We notice now, when I say the student wrote change in mass, this is the student data right here. These are actually negative numbers that show up on the balance. How is it possible that you get negative numbers? Zinc doesn't have an effect. So the zinc salt doesn't have an effect. But the other ones, for some weird reason, make the balance record negative numbers. Does anybody know why? Because there's a phenomenon in chemistry. How do you know whether a metal is magnetic or not? It has to do with your electron configuration. If the electron configuration of the atom or the ion has electrons sitting in orbitals by themselves, these create magnetic fields in chemistry. So now those compounds are going to be affected by a magnet. So you're going to prove which ones have the most unpaired electrons based on the electron configurations that you wrote. So for example, manganese will have a total of 5 unpaired electrons. So when you take manganese 2 chloride and put it on top of that little bridge, it's going to create the most negative measurement on the balance because it's pulling the magnet upward with a force. The more unpaired electrons this salt has in its cation, the greater the pull. It's called paramagnetism. What about things, important concepts like intermolecular attractions, polarity, ion dipole? When we do these experiments, we do it from this little kit. It looks like this. You can easily build something like this. There's a piece of plastic with graph paper underneath it. So you can see the little boxes, right? So we're going to take 4 chemicals. Water. Notice they all have something in common. Water. Ethanol. 1 propanol. And 1 butanol. They all have something in common. They have OHs on them, which gives them hydrogen bonding. They also have something else in common. They all have what we call London dispersion forces, right? What else is true? Well, their polarities are going to be different. So how are you going to test all these things? Well, what do you need? Well, the first thing we would do now, in an AP group, they don't get these little droppers. They get an actual 0.5 milliliter syringe with a plastic tip on the end. And they measure exact volumes of the 4 chemicals. And they measure how far it will spread on this polyethylene material. Polyethylene has no polarity. It only has strong London dispersion forces. So misconceptions. A chemical spreads based on the similarity of its intermolecular forces at its surface. So the chemical that has the greatest London dispersion forces will spread the most. So which chemical do you think spreads the most? 1 butanol, 1 propanol, 1 ethanol, or water? Professor Govardhan, I think you know the answer.
Butanol.
Correct. Why? Do you know why?
It's the least polar. Yeah.
Yes, but
Most
that's not why
hydrophile.
it spread. See, you gave me the Regents answer, New York State Regents answer. The correct answer is because it has the greatest London dispersion forces. Why does it have the greatest London dispersion forces? It's the actual opposite of what you said, right?
Yeah,
Because it has the most protons and the most electrons.
Yeah.
The more protons, electrons a molecule has, the stronger its London dispersion forces. That's important. What happens is, on a Regents exam in New York, as soon as we receive water, we tell the students that's the answer, right? But in this case, we're asking specific questions. When you testing the width of the drop, you're testing which one in this experiment has the greatest London dispersion forces. Now, water has the weakest London dispersion forces, but the greatest polarity. So it won't spread, it will adhere to itself. You with me? That's important. because then another experiment we'll do, we'll take these little these like baby beakers, and we'll count how many drops does it take to fill one of these little baby beakers. And that has to do with drop size. But drop size is affected by gravity. So what you would do is count the drops and then divide by the molar mass of the chemical. And you get a relative measurement of IMF. But then what we do is we take a little capillary tube and we stick it in one of these beakers and we measure the rise of the liquid up the capillary tube. What's that measuring? That's a direct measurement of polarity. If you take the rise and divide it by the molar mass of the chemical, you will get ion dipole attraction. So that's going to tell you which molecule is the most polar. Who do you think rises the most up the capillary tube? The answer is
Water.
water. That is correct, right? And then we can play around. We say to the kids, okay, we put it on plastic. Take one of these glass slides and put it on top of here and see if the width changes. Does the width of the drop change if you put it on glass? And the answer is yes, because now the glass has ions in it, and now the ion dipole attraction is going to affect the width of the drop. Another key difference. We took all my crucibles and threw them away. We don't do any experiments in crucibles anymore. Why? Because I hate crucibles. They're hard to manage. You need the clay triangle. You need the ring. You need the stand. We stopped doing that. And then we found that in my classes, we're doing more synthesis reactions, decomposition reactions than we ever did. So for example, your percent hydrate. In my class, each group gets their own hydrate, and they do the experiment in less than 15 minutes. We do empirical formula. We synthesize, instead of magnesium oxide, we use manganese 2 chloride, for example. How do we do it? Get rid of the Bunsen burner. We start with these little, what they call butane burners. The butane burners are really safe. You turn the little knob, you push the button. Then when you're done with it, you turn off the knob. You say, Mark, what's the big deal? Well, if you ever take out a Bunsen burner, you always got to have Valkyrie music in the background, dun, 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 because they got to first get it to stay flat on the table. Then they got to close the little valve. Then you got old school teachers with the igniter, igniting and getting sparks all over the place, and they're using propane accumulating on the table. Those are safety hazards. 31 years, I'm not dealing with those safety hazards. So what we do is we take out a butane burner and we use glass test tubes made of Pyrex, right? Pyrex was invented to do synthesis reactions at high temperatures. So we take Pyrex test tubes and we take a little piece of manganese, we put it in the tube, we weigh the tube empty, then with some manganese, we get the mass of the manganese, we add hydrochloric acid to the test tube, we get it to react, and then we heat off all the water. When we're done, you know what's cool about this? It has color. When you do manganese oxide or magnesium oxide, it's white. It's not very entertaining. Kids love color. That's the big deal. And then when we cool it, we use what we call a heat sink. We take an aluminum can that I cut the top off, and they just put the tube in the aluminum can, and the aluminum conducts the heat very quickly. So the test tube will cool a lot faster than a crucible will, where they start asking you, you think I could touch it? You think I can move it, Ms. Langella? Well, they just touch the can. If the can's warm, they can't touch the test tube anymore. Once the can's not warm anymore, then you can take the test tube out. And you can see the little manganese 2 chloride inside the test tube. That one move of changing the way we do the labs cuts 40 minutes into 15 minutes. We do easy experiments with a large test tube and your precision duster you can buy in an electronics store. We give them the percent of each element in the chemical in here, and we use these kits like this to get molar mass, which eventually they can get molecular formulas. We do a lot of gas collection over water. That's a big topic on the AP.
Hey,
To
hey,
do
Mark.
that, though.
Hey, Mark.
Question? Yes.
You've shown us a whole bunch of things that have been really great. And I'm wondering if maybe we can take a pause for a second and see if
Sure.
anybody has questions on what you've already talked about.
Absolutely.
It's kind of hard to remember all the different things right now.
All right, so if you want to like go through what I showed you so far, so the key thing is about change, right? So let's go back to distillation. Any questions about the distillation experiment? Pretty straightforward if you get this. Yes, sir, Kobe.
Yep. I had a general question. Like, do you have like a book or a handout or like handouts or whatever?
Yeah,
Like,
I'm going to show you at the end. I got online every single one of these labs that you could download.
okay, got it.
Right, and I'll show you where to go. Right now, my goal here is to show you the idea and you to say, how do I build that? Right, and so basically what you got here is plastic test tubes. Plastic tubing with connectors. This is a L connector, and up here there's a T connector. Because in the T connector, there's a wire that's measuring the temperature, the thermocouple wire that's measuring the temperature of the vapors up here. And then I got a 2-hole stopper, right? One has a piece that I put glue in the wire in that permanently stays in the stopper just for this experiment, right? So I'm measuring pot temperature and vapor temperature at all times. Because in the experiment, we tell you, collect the fraction of vapors between these temperatures. So they collect 3 fractions of condensed liquid in this cooling tube.
So
I had a question about that.
Good, go ahead.
Can you use a single piece of flexible tubing and cut a hole in it to put the thermocouple in?
The
and
answer
just
is
tape it?
no, because plastics will expand, right?
Okay.
So if you have technically, here's a great question, Kara. Technically, if you got latex tubing, right, you could do it because latex tubing, when it's like a rubber band, right, will create a seal. That's a great question. And that's something you're going to have to experiment with. So what I found with a T connector that's the right size for this tubing, you could stick the wire right into the T connector. And then on the top, you just glue it and it stays in there forever. Any other questions on distillation?
Mark, just a general question. How are you going to do these labs this year? Are you worried about like using equipment with students? Are you going to show them virtually? What are you going to do?
Okay, so this is a distance learning question. The answer is I'm doing these from my house because I'm not going back to the classroom because I got heart disease and I'm a type 2 diabetic. So what I'm going to do is I'm going to perform this experiment and it's going to be connected directly to my computer, which will be displaying the data collection.
Okay.
Right? One of the things that I will do live is I'll take these fractions and I'll light them. If they burn, that means they have more ethanol than water in it, more than 50%, which proves the separation was correct. And what I will do for them is take the density of what came over, because in the lab, when you get the lab write-up, from the density, you can determine how much ethanol is in the mixture.
Yeah.
Yeah. This is a classic. The kids love this. And a lot of teachers don't do it because they think they got to use all that sophisticated glassware to do the distillation. Remember that all rules apply. You need boiling stones in here, just like you do when you do it with a regular glassware. Again, this is not used for oil refinery. This is not used to find a cure of cancer. This is used to separate ethanol from water. That's what I'm trying to tell you. Because that's why we spend hundreds and hundreds of dollars on the ground glassware, because that you could do some sort of oil separation if you had to. Questions about chromatography, column chromatography?
I have a question, Mark. So I actually got this from you.
Oh, yeah, and that's right. Now remember, you were looking for packing, right?
Yeah, right, exactly.
Right.
So I have a question because, first of all, you had mentioned certain dyes. I didn't have access to those. I used red and blue food coloring, and it didn't seem to work that well.
There's a bunch. When you say red and blue, there's about 12 reds and 8 blues.
Right.
And each of them have different molecules and different polarities. So the one that works best, blue 1 and red 3.
So you know what would be really useful, because I actually went online to try to find those and I couldn't really figure out what was what, is maybe on your website where you have this. You could maybe give
In
them
the
an
lab handout,
where
it
I
actually has
find
the,
those.
where you buy them, you saying?
Yeah, where we could get those particular dyes.
My problem is 31 years ago, I got a small little bottle of red 3 and blue 1, and I'm still using it. You know what? You could have them when I'm done. I'll hand them to you. Because if I
Awesome.
can get back into them, I'll hand them to you.
And
But I have to
think
tell you,
other
if you
versions.
take, listen, I'm going to tell you the secret. Make it cooler. Take a step beyond. Go buy purple Skittles, right? Go buy purple Skittles. Take a whole bunch of them and throw them in a beaker with some methanol. I said methanol, I'm sorry. But that chemical that's like methanol, right? And what will happen? The dye will come off the Skittles, right? And then leave it in the beaker in a vent or out next to the window, and the methanol will evaporate and will concentrate the purple. Guess what's in that? Red 2 and blue 1.
Awesome.
And now you got your purple dye. That's actually cooler. But again, in the pandemic environment, how you going to do, you know, when you have them every day, you can show it to them or whatever. But once we're over this thing, that'll be the cool way to do it. And here's another cool thing. The packing, right? You could take my next design of this is going to take a Pasteur pipette, right? Or 10 milliliter garbage syringes, and you put cotton on the bottom with some sand and the packing. That's how we did it in the old days. That hasn't changed. That science hasn't changed. So you could easily have the kids create this if you wanted to.
The other thing that I ran into, Mark, was that I ended up needing to put the ethanol through many times. I had to keep taking it apart because it would fill up the little container before the any suggestions on how to manage that?
Yeah, it has to do with the polarities. There's a whole science. Chromatography is a big science field. So what happens is it's all dependent on the eluents you're going to use, right? And now if your packing is is a low polarity substance like C18, right? It has polarity. It's sand with carbon chains on. So once they throw the carbon chain on, the polarity goes down. Now, Flint, for example, sells the pre-packed packs. So you could just get that and plug that into the top of that setup and do the same thing with their stuff. You don't have to pack your own, and they're not that expensive.
You said
But
Flint.
the only problem with this is once you use it, you got to wash it. You got to clean it out with an eluent. So next year, you don't have to buy a new set. You use the same ones. But I want to show you, that's all great questions. We could do that in the breakout coffee room. We could go through, I'll take out my lab. We could talk about 1,000,001 variations that you could do. All right. Any questions about the LED lab, where you're talking about electron transitions? Technically, you could go buy some Christmas lights and do this with Christmas lights. You don't have to have this contraption, right? But you do have to measure the voltage across the LED. And when you're dealing with Christmas lights, that could be an issue, right? These are LEDs you plug into these contraptions. You know what this is? What is this on the right?
Noticeable.
This is your old medicine container that you threw out in the garbage, okay? You know what this is on the left? This is the plastic that had the electrical tape that the electrician throws in the garbage. That's what recycling means. Take something that's been thrown out and build and use it for something else. These are great containers for storage. These are the best containers on the face of the earth, the ones on the right. They're FDA approved. That's how great they are. Any questions about this lab? I think this is the coolest one out of all of them so far. That you can prove electron configurations. I don't know what experiment you could do that does that. But this one,
I love
on target. On target. It's like the #1 seller. And the AP workshops, they always do this one after that. Because
Right.
what other lab are you going to do to prove Aufbau's diagram? This is the only one I can think of. And this comes from an old demonstration.
Yeah, this was great. And Mark showed me how to. I didn't even purchase that one. He showed me how to make it myself. But
Yeah.
it's nice if you don't have the different chemicals. I got little vials and I put the chemicals in myself. But if your stockroom doesn't have it, than getting it from you guys is.
No, we're not gonna. We don't sell chemicals. All
Okay.
we do is we sell the vials with the labels on them.
Okay.
Right?
Yeah.
All we're doing,
But
all we do
great.
is to
It's a great
support. If you don't have time to build it, that's the only thing that we do. So I'm promoting. I'm saying to you, you build it. Save you if you have the vials already. Tongue depressors, you can buy them at Rite Aid, right? You know what I mean? You could get construction paper anywhere. All we're doing is building it for you and put it in a box if you want, ready to go. And you would put the chemicals yourself.
Yep.
Same thing, same idea with this stuff, right? Anybody can get clear plastic plates and put. Now, be careful though, because polystyrene is going to have a little different polarity than actually still would be nonpolar. Polystyrene. You can use polystyrene. Polystyrene plates with graph paper underneath, and you're in business. The cool part about this is this piece right here. These are experiments where we're collecting gas over water. Old-time teachers would have on their wall, sitting in the school, these things called idiometers, big long tubes to collect gases. You know what? If you're lucky, maybe you'll take it down once in your career to use them. I can't, because if I do something like this, my Regents kids, they'll be smashing those things on the lab bench, okay? So instead, we use this as your iodometer. This is a 60 milliliter syringe with a syringe cap. This is, you know what this is? Tennis ball can container that the tennis coach throws out in the garbage. You take the cans and you use this as your water bath. And you take this syringe, you immerse it into the water without the cap on, and it fills up with water. Some psychopath figured out that the headspace here is 1.2 milliliters. So whatever you read on the meniscus, you add 1.2 milliliters on the 60 milliliter syringe, and you know exactly the volume of the gas you collect. You create a J tube. Now, there's a lot of 101 ways you could do this. What we'll sell this piece here to save you time and make it, but you can get plastic tubing connected to, you know what this is? I'll tell you, here's the secret. It's one of these things. You can't see without the background. It's one of those little plastic droppers that you have, the thin stem. I took a match, lit the end, and made it turn into a J so you can collect the gas with it. Okay? It's not that kind. This is a one-hole stopper on a test tube. What can you do with this? Well, remember I told you we don't use graduated cylinders. I could take this test tube, put a piece of aluminum in it, throw some hydrochloric acid in there, collect the gas. And I am just like our forefathers. How did they get the molar masses of the elements? That's how they did it. They collected the hydrogen gas. They used Dalton's law of partial pressure to get the pressure of the hydrogen by subtracting the vapor pressure of the water. And they were used stoichiometry to figure out what the elemental masses were. That's how our forefathers did it. So the idea is all there in sin. I just modernized it with common plastics. And my favorite part, it fits in a tennis ball can. Easy to store, upside down, sideways, whichever way you want to store it. You know the butane, when you go to the dollar store? When you go to the dollar store and you get the little igniter for $1 at the dollar store? Well, next time, get one of those and rip it apart. Just rip it apart and look at what's inside. You get this little butane source, right? That's not butane. That's a lie. That's not butane in there. It's a mixture of butane with something else. Either they mixed it with a little bit of pentane. That's possible. Or they might have had some propane in there a little bit. You think they did fractional distillation so they could give you your $1 igniter with butane in it? That ain't happening. But you know what's cool? You're going to prove, is it mixed with some pentane or is it mixed with some propane? You could prove that by determining the molar mass of this gas. How? By collecting over water. So this is the setup. So it all starts out like that. That's what it looks like. Other major change. Take those big gawky calorimeters and throw them away. You're wasting time. You're wasting time. You can buy these little foam block calorimeters from Flynn. Flynn's the big seller because he got the patent on it. This little, you know, I didn't buy this. I made it because the guy who sold the idea to Flynn was my mentor. He took foam insulation from Home Depot, sliced them up and drilled holes with wax coating on the bottom. Sold the idea to Flynn. Now he's retired, still collecting checks from them, from the idea. So he gave me all the excess. I still have them 31 years later. So you buy this one set and you keep them forever, and you do all your calorimetry experiments in this little foam cup using maximum volumes of 15 milliliters. That's it. You never go beyond 50 milliliters. So what do? We take pieces of magnesium of different masses. I'm actually evil. I tell the kids allow them to measure a 16 centimeter on an analytical balance in AP Chem. And then I say you're not allowed to weigh the magnesium again. And they cut them into different pieces, and they use factor label method to figure out the mass. And then they use syringes to measure out volumes. It's all about mass, but we're dealing with mini mass. We're measuring smaller masses. All our labs, we don't use burettes to measure volumes. In fact, what we try to do is substitute devices called syringes that they use in the medical field to measure volumes, to measure the volumes they need for the labs. So these are high-level, sophisticated experiments. You can see all the plasticware. Now this glassware, you know why it's on the side? I gave it away. I gave it away. The only ones I kept was a 2 milliliter one and a 0.5 milliliter one. I gave all that away. By getting rid of the burette, we get from 1 titration to 7 titrations, right? So we take a 1 milliliter, notice it's marked in blue, no more stopcocks, no more broken tips, no more stands, no more burette clamps, all gone, all gone. And we do the same experiment. I'm gonna do one live if I have enough time. I don't know, I'm gonna run out of time.
Question, Mark. Sorry to interrupt.
Yes.
Because I know, like, right, in the previous discussion, the safety presentation, right, you did ask about, not getting the chance to do, use some of these, crazy, like, solvents like methanol, and the fact
Correct.
that, because, that's what really excites kids about chemistry. Now, so here's the case, we're doing like experiments, like not using like the traditional like apparatus, right? So burettes and whatnot. And let's say, your kids are all like super, psyched about chemistry, they want to do more in college. I mean, do you worry that kids then get it and they're not able to know how to use a burette, or like, does that affect their future chemistry educational progress?
Okay, you know how
does it make sense?
Kobe, I have to tell you something. I'm coming to the end of my career, right? At the end, Kobe, how you did your job? You ask the kid,
What?
At the end of the year, this is how I keep score. If you look at my AP grades, you think I was a rock star. But that means nothing to me. You know what matters? Hey, kid, what are you going to major in? Oh, Mr. Langella, I think I'll major in biochemistry, chemistry, engineering. And I go, why? You think it's because of my personality they're doing that? They always go, the labs.
Right.
Right? And the more they do, the more they like it. It's addictive.
Very true.
Okay? So what happens is the Frankenstein effect. You know the Frankenstein effect?
No, get it.
Sure you do. So when you get those big pieces of glass apparatus set up, like remember when you might have taken organic chemistry in college, if you're a chemistry major, and you built that distillation apparatus, and that feeling you got building it, that's called the Frankenstein effect.
Gotcha.
Every time you watch a Frankenstein movie, that's the first thing they do. They put that in the background, right? Because that makes you feel like you're a scientist.
Right, that's right.
That you will lose, but you will gain by doing 50 experiments instead of 7. That's what I'm trying to tell you.
Yep.
So,
Okay.
But you got to give something up.
Right.
The homework questions become the labs. So you incorporate, they have ownership of their numbers that they're doing the homework question with, rather than the one that you assign from the textbook, which are fake and never real numbers that you get in the experiment. That's what you gain, Kobe. That's what you gain.
Sounds good. Yeah.
So you see, these are kind of titrations we do, right? Now, even in my Regents class, they do this one right here, the standardization and the preparation of sodium hydroxide, but mini scale, not macro scale. Voltaic cells. This is what our voltaic lab's doing. there's 1, 2, 3, 4, 5, 6, 7, 8, 9 cells, and they create multiple systems, multiple voltaic cells, and then they put them in series to light up an LED. You can't do that macro scale. It takes too long. Electrolysis. We do a whole bunch of electrolysis experiments, but we do them in these tiny little U-tubes that emulate what our forefathers used to do. But we make these little tiny tubes. Now I don't do them out of glass anymore because I used to make my Regis glass, do glass bending. That takes too much time. Now we do it out of plastic. I bend the plastic, and we do it in plastic, where you're using little pencil graphite leads as your electrodes. I'm sure many of you have done variations of this one, but that's the concept. That's not how we used to do it, but that was okay to mini scale that one. What about mini scale some other ones? And then the last experiment that I do in my class is what we call the final. We create a baby Hoffman apparatus. How do we do that? We take a baby syringe and we make it into an hydrometer, and we immerse it in a sodium sulfate solution, which is this big, what do you call it? Tube. You can do it in a test tube if you want, right? And what we do is we immerse this and cap it under water. We fill it with the sodium sulfate. And then we hook that up to a 9-volt battery. And we notice if we put indicator in here, we get different colors because the chemistry that happens on the outside is different than the chemistry on the inside. So we collect the hydrogen gas, and then they use math to figure out what gases are being produced outside the hydrometer. So where are all the labs? If you go to this website, right? Let's see if I can show you this. At the website, under each of the products is a lab that goes with the product. Let me just, I gotta change the sharing, right? Hold on.
Can we put that in the thing in the
Yeah,
website
yeah,
address?
because I know you guys got to go. How do I do that though? You're gonna have to help me.
No, just tell me. I'll type it into the chat.
Yeah, so it's mini-concepts.com. And if you go to if you go down the front page right here, it tells you. Now remember, I'm an AP consultant, so this is what the AP wants. These are the labs they have to do in the college course. And underneath it, I listed every single lab that I do, right? If you go to the site, the actual where this product is, you click the product, it will take you to its own page that has underneath it the actual lab. You'll see a little link that says lab on it. So like I got to take you to the site. At the bottom of the description, you typically would see a lab that comes with it. I got to make sure they all have it, because if you guys go there, you're going to be looking for that. I will have the link that has the labs that go with that kit. This one doesn't have one because it has it's with the distillation one. Like example, this one. Let's do this one. You'll see the word lab. See the word lab? You click that. And it shows you the experiment. How to build it. And the whole thing that goes with it. That's where the labs are listed. Go to the product. At the end of the product description, I'll have the lab that goes with it. Now, these are just examples of what you could do with it. You could come up with other ideas. You got it? You want to see a micro scale at work? How it works really fast? Do we have time to do that? I don't know. Or do we have to go to the? I could do one in less than 15 minutes. Ready? Let's see. I'm going to change my my camera so you can see that I'm not making anything up. There's no magic tricks or anything under my sleeve. All right, let's go see. I'll change the camera. So I'm going to change the camera to this. I'm going to change the background. Hold on so you can see. So just before I started, okay, just before I started, I took, this is a classic one. I took some calcium and put in some water. If you take some calcium and put in some water, and you guys see this? I'm not crazy about how my camera's acting, right? I put some calcium in some water and left this open. And what's going to happen? Calcium reacts with water, and all of a sudden I notice a precipitate's formed. What's the precipitate? It's calcium hydroxide. Because calcium hydroxide doesn't dissolve well in water.
Hey, Mark?
Yes.
Mark, we're not really seeing what you're showing us. We're still
Okay.
seeing the
You can flip. You can flip your
okay.
screen
I'm sorry.
in the top right-hand corner. You can flip it so his screen is
Go to
big.
speaker view. Click speaker view.
Okay.
Zoom.
Whoops. Okay,
Can you
so
see that? Can you see what I'm showing you?
okay, I'm not sure how to make it so that it shows.
All right,
the
I
speaker.
got a way to do it. I was trying to avoid using this program because it's a little glitchy. I brought this document camera that came with a program that, for some weird reason, it's flickering, which I can't explain. But let's give it a shot. Hopefully, it will. Let me change this.
I would like to know how to make the speaker view highlighted.
On the top, if you click speaker view, it only shows who's speaking, enlarged.
Oh, I see. Okay, yep, got it.
Oh, all right, hold on a second. Let me. Shut this off. Change it back. Enlarge. Come on, buddy.
Oh, so Mark, I also just want to mention that you've got about 5 minutes left.
Okay. All right. So what I'm going to do is I'm just going to talk you through how easy this is. Okay. Let me just get the camera to show you the image enlarged, so you can see it. So I took some calcium, and wrong one. And you see this?
Yes.
Okay, so I took some calcium and I put in some water, 25 milliliters of water, and kept the cap off, and the gas was being produced. Okay? This is a typical example of mini scale, right? And now what I'm going to do is I'm going to decant the liquid part off of the solid that's sitting on the bottom, the precipitate. How are we going to do it? Mini scale. I took a syringe, 10 ml syringe, I put some cotton in here with a plastic tube on the end. I'm going to stick that in this test tube, and I'm just going to pour the liquid part off. Okay? And it's filtering, mini scale style. The liquid's going through the column, through the cotton, and I would collect this, right? This is why I didn't want to use this program. It has this weird capturing feature, which I don't know why it automatically goes on. But what ends up happening? Well, as it goes through here, and I collect it in the tube, you can see it coming out, drops coming out. All you need is 1 milliliter to do this experiment per trial. So this will last everybody at the table to be able to do 2 trials. That's it. So you can see the liquid collecting in the bottom of the tube, right? What I would do now is take one of the syringes that's only designed, blue is for bases, right? Only. I would put it in this tube and I would fill this up to 1.0. Oh, I'm sorry. Well, I was avoiding it. I'd fill the syringe up to 1.0. So this is the base that I'm going to test. And then I get my red syringe that's only for acids because it's labeled red, and I'd fill that up with a known concentration of a weak acid, strong acid of 0.05 molar. Again, mini scale, you don't need concentrated acids, right? And here we go. We're ready to do a titration in this little tiny plastic cup. Now, some of you are looking at me like I'm crazy. But when you go to an analytical lab and you ask them, where are the burettes? They're going to look at you like you're crazy because there's no burettes left in an analytical lab. And they go, yeah, I got one in the drawer for nostalgia. Then he goes, well, how are you doing the titration? You go over it, it gives you the micro titrator. You open that up. Guess what's inside? A syringe. That's what I'm trying to tell you. So I'm not going backwards with technique. I'm going forward with technique. So we're going to do a titration really fast. I could do this in the coffee house where I could titrate this solution. Look how much I have. I have enough for the whole class to do in this test tube right now because it's mini scale. And I'm going to do it in this tiny little cup with my indicator and get my endpoint in less than 10 minutes. And we're all doing it at the same time. So we get 4 trials, 10 minutes. Now the onus is on them to do homework at their house. What are they going to calculate? They're going to calculate what we call the KSP, and they're going to calculate the molar solubility from the KSP. And then I'm evil. Molar solubility, we're going to convert it to grams per 100 milliliters. And then we're going to put it on a solubility curve, and we're going to see if we are at equilibrium or not. That's the kind of thing you could do when it's mini scale. But macro scale, you're talking 80 minutes to do the same experiment. So by converting, taking some things out, just a couple of moves. The big one's the syringe. That I'm not going to lie. That's a big move. About 23 years ago, 25 years ago, a good mentor of mine, a friend, said, if we go mini scale, we could do twice as many. And he showed it to me. And when he showed me the data he got and how accurate it was, I was like, you got to be kidding. And then I realized, and that's how we converted. Questions on mini scale. Again, it's going to directly affect the environment because you're reducing the amount of chemical. And we don't throw things in the sink. We'd rather shoot it. That's another thing that people don't tell you. You're better off putting it in the garbage bag, mini scale volumes, than throw it in the sink because that's going to get incinerated. The other one's going to go right into the water tables. You know what I'm saying? So again, it's mini scale. You could shoot what's left over into a garbage can, right? Now at school, I'm not gonna lie, we have little baby glass beakers. We have 5 milliliter glass beakers and 10 milliliter glass beakers that we substitute the plastic with, because you could easily wash it out and do it again. Do it again. When I'm on the road at workshops, I bring the little baby plastic beakers. But if I was a teacher that didn't have their own room, I'd go opt with the plastic beakers so that I don't have to deal with the glass. Any questions on mini scale? I could do the lab in the little coffee house if you want, but I'm sorry. Every time I do these things, I always run out of time. It's because I got a lot to share. I get share too much. Yeah.
Well, your enthusiasm, Mark, just comes through so clearly, just how excited you are about it.
Well, it's because I believe in it. If I didn't believe in it, it wouldn't come through. I'm not a good salesman. I only can sell what I believe in. Like if you talk, it's like going to a Ford dealer and he's got a Toyota in the parking lot that he drives. I'm not like that. These are labs that I do and have been doing. You know what I mean? And I have a criteria. They got to be Bobo proof. That means you could be the worst lab person on the face of the earth. You're still going to get data that you're going to do homework with. It has to pass that test. If it can't pass that test, I won't do it. Like Ms. Vogel brought the chromatography thing, right? But she didn't follow the exact procedure that's in the handout that I'm going to share with her. Now she's tinkering with other dyes. Now you got to tinker with the packings because the one that I wrote off is bubble proof. If you do it exactly like I told you, it's going to work. But if you tinker with it, I can't guarantee that. You know what I mean? Because these have been tested and modified and adjusted to deal with whatever we got to work with.
Sorry, Mark, one quick question.
Don't be sorry. That's why I'm here. You know, they're not paying me to do this. I'm doing it because I want to.
Awesome. Thank
Ask
you.
as many questions as you want. That's why I'm here.
Yep. Great. Like, can you show me how to access the lab handouts again? I couldn't quite figure it out. Like, once I get to the website, like, how do you actually get like those?
Yeah, you got to look at the products, right?
Okay. Well,
I gotta put that
share
on the screen.
screen. Okay.
I'm not 100% sure about every single one, but if it's not there, you send me an email and I'll put it there for you.
Wonderful.
Okay? That I will tell you, because that just will force me to adjust the web page. Okay? I'm gonna go to the mother hub of my thing here. I'm gonna walk you through it so you can see. So if you forget, my organization that I have a non-for-profit and a for-profit, two different divisions. The profit one is involved with the kits. Okay? So if you go to powista.com that you see on my shirt, it brings you to this webpage. Under here, there are tons of different things that I unfortunately am involved in. Right? But they help pay the college bills that I still owe. So if you go to mini contests right here, right? It brings you to the page that Ms. Vogel put up. If you go to, there's a lot of ways to get to the same thing. So let's pick the first thing. But this is a newer product, so I'm not sure whether I put up the Bunsen Burner Lab. I'm not sure. But I am sure that some of these other ones, like this one, has a lab. If you click the title, it's bringing you to our server that has the lab listed and has the product page, right? When you go down the product, it's telling you what you could do with it, what you could teach with it. Then at the bottom, right underneath the picture, you're gonna see either it says lab right up. This one, if I click this, watch. It's going to the server to go get the lab that we wrote up for it. And it's going to display it right there. Okay. So you got to go to each of the products.
Yeah. So I tried to download the one for the manganese 2 chloride one, but I don't think it's even like you can't really click on it. I don't think.
Well, once you click on it, it opens like this. You have it in your possession right now. So.
Like I could not even open like the link. There's no link to actually like click or open open.
That was the one I opened before, was it?
Sorry?
That was the one I showed before. That was the first one. All right, let's try it. I'll go right now.
Yeah, that'll be yeah. Let's see.
This one right here, right?
The manganese 2, right? The
the one you make it. I'm sorry.
The empirical.
Yeah, that's I don't have that on here. You gotta email me. We don't.
Okay.
That kit. It's listed as the lab I do, but I don't have a kit for it.
Yeah. So I'm actually referring to the lab handout. Like.
Yeah. You're gonna have to send me an email.
Okay. Now email. Okay. Cool. Now email. Okay.
Yeah. We don't sell a kit for it because there's nothing to sell. When we sell your test tube and a holder.
Right.
You know what I mean?
Yeah.
So for that, just send me an email and I will send it to you.
Okay, cool.
In fact, you know what I'll do? I will give it to Ms. Vogel. How do you pronounce your first name correctly?
It's Jerusha.
Jerusha. And that's what everybody calls you, Jerusha? That's why I use Mark, because Marcellia is too complicated.
Yeah, I noticed that in the thing. I was like, oh, his first name isn't Mark.
Jerusha. I will send it to Jerusha and she will put on whatever this Google thing that they have.
Okay, perfect.
All right. So we'll write down whatever ones that you want. You tell me which ones you want.
Okay.
That I don't have up there. So what I want you to do first is I want you to go to my webpage, right? That I just showed you. Look at the different kits and products. See which ones I don't have, and I will send it to you.
Okay.
This way we'll kill two birds with the same stone.
Perfect.
Manganese chloride synthesis. You got it. That's a good lab. That's a classic.
Yeah, it looks good.
Yeah.
All right. So I think we need to
get out of here.
Lunch before the next session.
Yeah.
And thank you so much, Mark.
I'm gonna hang out in that coffee room thing while I'm down here. Is there a way to get to the coffee room? How do you get to that coffee room thing?
Yeah, so you go back to the link that was in the keynote address.
Right.
That
And I'll
one.
hang out in there. So
Right.
if anybody has more questions they want to ask me, or Kobe, you come up with something else.
Yep.
Well, if you're not going to one of these other ones, I'll be in there. You can just ask me.
So
Perfect.
just so you know, the coffee house might not be open right now because it's not being manned during lunch, but starting
okay.
at 1:15, that will be open as the coffee
Okay.
house.
I'll be in there. I'll be in there.
Okay.
Meanwhile, I'll send you, Jerusha, I will send you the labs that he wants. So you can take
Perfect.
it. All right?
Perfect.
Okay.
Thanks so much.
You're
Thanks so
welcome.
much, Mark. This was really
No
awesome.
problem. No problem. That's why I did it.
Yeah. Yeah, thank you.
You're welcome.
Many thanks.
Thank you.
All right. I'm going to end it now. Mark, thanks again. I look forward to getting some emails from you about whatever you're planning for this fall.
Yeah, and I will send you the as many links as I can give you. As many as I can. All right? Okay.
Wonderful. Thanks so much.
Bye-bye.